Well, before leaving the idea of Snell's law and refraction of light, I don't want to beat it to death, but I want to look at Huygens' principle, showing how our good buddy Huygen can help reveal how this refraction occurs. So here we go. We got the refraction from one medium to the other, 1 to 2, theta 1, theta 2, and here's our wavefront coming in. We got a segment from A to B, and it's at this point at A, it's impingent upon the medium, and so things slow down. So the time interval from A to C, as the little wavelet, Huygens' principle is the idea of the infinite number of little wavelets along here, point sources of disturbance. So we're just looking at the one at A. A certain amount of time, the wavelet moves to C, and in that same amount of time, produced along at B, it moves over to D. Okay, and so then we have, connecting the tangent lines, we have this distance is velocity times time. Well, what velocity? Well, the velocity in the second medium number 2. Likewise, in medium 1, we have v1 times t. Obviously a greater distance, so obviously a faster speed, because it's the same time. And so this is how the wavefronts look. But now we're considering that this is light instead of just water waves. So the speed changes when it hits the interface, moving v1t in the faster, v2t in the slower medium, and because of the way the tangent lines connect to the curved wavelets that come from the point disturbances, we got those wavelets arriving at A and B, going from A to B at the same time it goes from C to D, and the tangent line is produced. We see the line from C to D there with the two wavelets in question, and that's all lined up here. So anyway, hopefully that kind of makes sense with Huygens' idea. And the rays bend toward the normal. You can see why, as it bends down like this, you're really bending toward the normal. So that's, the ray is perpendicular to the front here, okay? If the second velocity is slower than the first velocity. Now just doing a little geometry again, this will be a recapitulation from what we did with waves in general. And let's look at this geometry again. So we have theta 1 here and theta 2. So we have theta 1 and theta 2. We're going to relate the geometry here. We actually see two right triangles. There's a right triangle, and here's a right triangle. These two right triangles, there's a right angle, there's a right angle. The two different angles, okay, these angles. But this is a shared hypotenuse right here, a shared hypotenuse. Isn't that special? So sine of theta 1, sine of this angle, opposite, which is this distance, over hypotenuse. So v1t over AD, opposite over hypotenuse. And sine of theta 2, v2t, the opposite side over the hypotenuse AD. So there you go. They both have the AD in them. If we divide sine of theta 1 over sine of theta 2, well, if you take this and divide it by this, the ADs go away, the T's go away, and we're left with V1 over V2. Now, we've already defined that V1, as related to the index of refraction, is speed of light over index of refraction in medium number 1. And same thing for number 2, C over N2. And so when we plug them in, the C goes away, and we have N1 sine of theta 1 is N2 sine of theta 2, or Snell's law. So now you will never doubt the truthfulness of Snell's law and the effectiveness at Huygens' principle to describe such a phenomena.